Okay, so we'll continue with the other, so we looked at the metrics of mixers, right? Conversion gain, noise figure, linearity and so on. So there is one more thing we left out for at the end of last class, which was what are called spurs. Okay, so spurs is basically a short form for spurious. So these are unwanted frequency components at the mixer output. Okay, so what will happen is, in general, so because in general you are trying to use the nonlinearity of the mixer to create your frequency translation. Okay, what happens is, along with this nonlinearity you will get other you will have other undesired nonlinearities which will cause other undesired frequency components. Okay, apart from that, you are assuming simple sinusoids going in. If you have higher harmonics of the RF or LO going in, you would have intermodulation between those components also. Okay, so in general you will get components at m omega RF plus or minus n omega LO. Okay, for all values of m and n. Okay, with up to the highest harmonics available in terms of linearity of the mixer or in terms of the harmonics coming in. Okay. So in general, this is very high, this is very tedious to analyze. Okay, so normally you let the simulator do it. Okay. Okay. So now, so let's. So in today's class, we'll start off with 2-port mixers, and then if we have time, we'll move on to 3-port mixers. Okay. So what do we mean by 2-port mixers? So remember that the mixer has 2 inputs. So the RF input, LO input, and it has the IF output, or IF, or in the case of a receiver, right? In the case of a receive mixer, it's an IF output. So 2-port mixers are those where so both RF and LO inputs are given to the same port. Okay. And this has some function f of Vn. Okay, we assume it has some small nonlinearity or so called soft nonlinearity. Okay, and we are going to rely on the nonlinearity to create your mixing effect. So let's just try to analyze it quickly in terms of a general transfer function. Oh, sorry, okay. So what will your output have? If your mixer has, so we have looked at something like this many times before, right? So your output will have DC terms, okay, it will have your harmonic terms, and it will have mixing terms, that is intermodulation terms. Okay, so let's look at each one and try to arrive at the desired output, and we'll see what it gives us. Okay. Okay. So where do the DC terms come from? It comes from all even order nonlinearities, right? Okay, how do you get rid of it? AC coupling. At the output. Okay. So you'll get harmonics of omega RF and omega LO. Okay. You get all harmonics. So if you have an nth order nonlinearity, you will get all harmonics. Okay. So how do you get rid of this? Let's assume that these are all much larger than omega IF. So you can get rid of them using filtering in a receiver. Okay. So now we'll come to the desired term. What are the desired terms? Are the IM terms. Okay, so those will be P omega RF plus or minus Q omega LO. Oops, actually P plus Q equals 2, so on up till N. Okay, so you'll get all intermodulation products. What is your IM2? Okay, P equals Q equals 1, so you get omega LO. Okay, and one of these is going to be your desired output. Okay, okay, these are your IM3 products, and these are usually undesired terms. Okay, so let's consider a general second order system, okay, and see what we see at the output if we give a certain RF and LO input. Okay, so let's assume so these are called square law mixers. Okay, so what we are going to assume is V out is C1 Vn plus C2 Vn squared. Okay, and we are going to assume Vn is Vrf cos omega Rft plus VLO cos omega LOT. Okay, okay, so first of all, okay, so what you get is you get square terms from the second component and fundamental terms. So the fundamental terms are nothing but C1 times Vn, which is Vrf cos omega Rft, VLO cos omega LOT. So those are just your LO and RF feed through to the output. Okay, the square terms give you three terms. One is so you're basically going to do Vn squared, so it's going to give you Vrf cos omega Rf t the whole squared, okay, plus VLO cos omega LOT the whole squared. Those are the square terms. Okay, those will give you a DC term and a second harmonic term. Okay, so the square terms give you Vrf squared, so this gives you DC. We have done this many times before, right? Gives you DC and 2 omega Rf, and this also gives you DC and 2 omega Rf. Okay, and you have it. Sorry. Oh, sorry. Yeah. Okay, and you have a third cross term. Okay, you also have a 2 Vrf VLO term. Okay, what does that give you? C2 times, okay, 2 what did we, so Vrf cos omega Rft, okay, actually let's call this capital V, shouldn't confuse with the other VLO. Okay, oh sorry, So it will give you a difference term and a sum term, right? So one of these will be the desired frequency component. Okay. So what is your conversion gain? It's your output IF amplitude VRF VLO, okay, over your input RF amplitude, okay, which is C2 times VLO. Is that clear to everyone? Okay. So what that means is, so your C2 is typically fixed. Once you fix the transistor bias and everything, let's say it's composed of transistors, for a given system C2 is fixed. That means that if you fix amplitude of your LO, then it's a linear mixer, okay, because the gain is linear. Okay. So what do we know? We want to get a square law device, okay. What do we know? What device do we know that is a good square law operation? Your MOSFET in the long channel, that's very important, okay. So long channel MOSFET. Okay. So let's consider it. So let's start off. So we want to give RF plus LO as the input, okay. So let's construct a simple, so this is your, let's say this is your drain load and this is your, let's assume IF is high enough such that you can do tuning at the output, okay, and so you have V bias, VRF and VLO, okay. So if you input something like this, so let's say you can add RF and LO through some kind of resistor network or reactive network, okay. The main problem with this is remember that we had problems with if your LO signal leaks through to your RF port. So this has very weak isolation between LO and RF. So let's see if we can, we still want to use a MOSFET, but let's see if we can improve the isolation a little bit, okay. Okay, so let's see how can we modify this. So output there was no problem. So effectively what is happening is you're connecting RF and LO in series, right? So it is very easy for your LO to leak through to your RF signal. Remember we had a problem when we considered the original mixer to be 3-port. Remember that your LO signal is going to be very large and your RF signal is going to be very small, okay. So what is going to happen is if you do something like this, okay, we were always worried about, so it's very easy for LO and RF to interact with each other, okay. Okay, so we are going to do it slightly differently. So let's say we give the RF at the gate. Okay. This is a LO. Actually, let's do it slightly differently. So you need two blocking capacitors, okay, and you need a bias voltage, okay. So this is slightly better because now your LO and RF signals are isolated through your CGS. It's still better than the previous case, but it's still not good enough. Okay. Okay. Let's assume a few things. R bias is large, it doesn't leak your RF signal and it doesn't have any noise. we'll assume that. Okay, so you choose that large enough. Okay. Okay, we're going to choose that the bias conditions and the length are chosen such that it's in proper long channel operation. Okay, remember that your short channel, so what you'll find is if you design a short channel mixer like this, it will show inferior performance to a long channel mixer. Okay. Okay. The other thing you want to avoid is subthreshold operation, because in subthreshold you know that the transistor characteristic is exponential, right? So you want to avoid that. You want to get a pure. Okay. So what is your current ID? Okay, that's your VGS minus VT the whole squared. Actually, I'll want to be careful. Okay, VGS minus VT the whole squared. What is your VGS signal? Is VRF minus VLO. Okay. Okay, so you have a bias component, right? That is your total VGS. Okay. Okay. So let's expand out ID. So we'll group V bias and VT. Okay. Okay. Now let's expand into three terms. Okay. Let's expand into three terms. The first term would be V bias minus VT the whole squared. Okay. What is that? That's your DC bias. DC bias current. The second one we'll choose. So what we'll do is we'll assume that this is one term and V bias minus VT is the second term. So the other one will be times actually let's 2 V bias minus VT times okay, this is the 2AB term. So what does this gives you? These are all constant terms. So it gives you your RF feed through and LO feed through to the output. Is that clear? Okay. Let's look at the third term. Okay, and this of course will give you again three terms. Okay, the first one is what is the first term? Okay, again you know, so let's call this A. Okay, let's call this B, and we get a the cross term. Okay, call this C. So again A and B give you DC and the harmonic terms. Okay. What does C give you? Okay. Again, you're going to write cos omega cos A cos B. You write it as the sum of the cosines and the difference of the cosines. Okay, so now we can calculate our conversion gain for this mixer. What is the conversion gain? So let's say one of these is the desired term. So the conversion gain is VRF VLO, half mu CX W over L VRF VLO over VRF. Okay. Okay, and what do we know about this term? This is actually the C2. Remember where we calculated for a square law mixer, it's supposed to be C2 times VLO. And remember that the characteristic of the mixer is basically just a square, right? It doesn't have C1V, it just has C2V squared. So if you compare this to the original C1Vn plus C2Vn squared, naturally this portion is C2. Right? So it looks good. Okay. What do we know about this conversion gain C2? So first of all, it's independent of bias, which is very good. Okay. But it does depend on temperature through the mu. Okay. So that could be a problem. Okay. So independent of bias. And of course the third thing is it's a function of the LO amplitude, which could be a problem in some cases. Okay, which means if you want a fixed conversion gain, then you need to control your LO amplitude very carefully. Okay. Okay. It's a function of the LO amplitude. It's a linear function. But what that means is you need to control your LO amplitude. We'll look at cases where you don't need to control your LO amplitude to a fine extent. That will come to next. Okay, because ideally you want it to. Okay, so let's say you're designing a mixer of 20 dB. Okay, so then this puts post constraints on your LO design. Okay, that means the signal coming in, your LO signal coming in should be of a fixed amplitude if you want a fixed conversion gain. Okay, we don't want to give that constraint. Okay, before moving on, let's do one more thing. We are going to calculate the same thing for a bipolar mixer. Okay, let's just quickly do that. What's the equation for a bipolar transistor? It's Is exponential Vb by Vt. Okay. So what you can write is, you can write this as IC times 1 plus. So let's say your input voltage is Vn, okay, and your bias voltage is some Vb. So if you write this as Vb plus Vn, Is Ex exponential Vb bias over Vt would be IC, the collector current, DC current, into 1 plus, then you expand out the exponential. Okay. Okay, what is C2? So now we'll start using it C2 easily, because any polynomial form you can directly use C2. This is IC because this is let's call this Vb plus Vn. This is your bias. Okay, so you have a bias and you have a Vn. So you can write this as Is exponential V small b over Vt, which is your IC. Okay, what is C2 then? Half Vn over sorry. IC over 2VT squared. Okay. IC over VT is GM for a bipolar transistor. So it's nothing but GM over 2VT. Okay. Okay. So okay. So let's say we want to compare the performance of a bipolar mixer and a MOSFET mixer. Okay. Let's see if we can write the into VLO. Yes. No, not Vn is much less than Vt. You are neglecting higher order terms because you know for a polynomial, right? We already found out that C2 is the one which gives you the desired term. Yes, that would definitely compress. Okay, so you're assuming that you're in the small signal regime. That is valid because you always assume that the conversion gain is defined at lower amplitudes where your linearity. See, remember that we have if you look at your fundamental gain, you have a linear region and you have a compressed region. You always define your this thing in the linear region, your gain in the linear region. Okay, so that is assumed. Yes, that is okay. That is okay. Yeah. So what was that? Half mu Cox W over L times VLO. Okay. So what we're going to do is we're going to write it. Yes.
For BJT, is it possible to bias VBE?
Why not?
Voltage biasing of a BJT is not at all, like it's very interactive.
Yeah. But that's okay. Basically, you need to do a current biasing, but it will have a certain VBE across it. See, here I didn't even say what this VBE is. It will be biased based on current, and it will have a certain VBE.
You cannot even modulate VBE by giving a
I'm not modulating. No, you can. Of course, you can. You can always give it at the base. You have a separate bias current. So you have the bias voltage plus signal going in at the base. You have a bias current source at the emitter.
But that, like,
Of course, that
has been very fine because it's exponential rise. What I'm trying to say is that little.
No. What I mean is the extra bias voltage will fall across the current source, right? That is what we do always.
Yes, bias voltage will fall across the.
Yeah. So we are not controlling the bias VBE in any case here. We are controlling only Vn, which is being given as the small signal VBE across for the bipolar transistor. Okay. Okay, we're going to multiply and divide by V bias minus Vt. So let me. Okay, so the 2 has to be included with that. Okay. Yeah, that is C2. You're right. Okay. Let's just try to look at this thing. Okay. So what do we know? Usually, for a given bias current, your GM of a BJT is usually larger than GM of your MOSFET. Also, VD side is usually larger than VT. So typically, as far as gain conversion efficiency, conversion gain efficiency is concerned, BJT is better than a MOSFET. Okay. So what are the issues so far with two-port? So one problem was isolation. RF and LO. Okay. And the other problem was underside spurs, because naturally by having a nonlinear system, yes.
Not exactly because dimension is kind of a convection.
Yes, that's okay. Conversion gain need not be in terms of volts over volts. It can be transconductance, it can be anything, right? It depends on what your load is. Finally, you will be, what I've assumed is, you will have a tuned load at the drain of the MOSFET or the bipolar, and that will have a certain RP, a parallel resistance. This current multiplied by that will be the overall conversion gain. So this underside spurs is a basic feature of the nonlinear mixer, right? You are using a nonlinearity to create this. Okay. So now let's move on and try to look at 3-port mixers. Okay. So first we'll look at what are called multiplier based mixers. Okay. So the idea is, so you have 3 ports for good isolation. Okay. And the other thing is, you want to ideally generate only the desired intermod product. Yes. Okay. Actually no, because remember that we defined a 2-port as output is some function of Vin. So the Vin is actually between these 2 ports. It's the gate source of the transistor, which is creating which is your input port. So effectively it's like this. So and one of these is, this is what we are doing. Okay, because the output input relationship is with the gate source.
They are also with reference to ground, right?
That is okay, but the signal, as far as the signal is concerned, remember that the transfer function of the transistor itself depends only on VGS. It is not reference to ground. Okay, so remember that this was f of Vn. Okay, so the transfer function of the transistor itself is with respect to the gate source voltage. Okay, so let's look at the simplest multiplier based mixer. So these are typically called often called Gilbert cell mixers. You will hear them using Gilbert multipliers. Okay. So because Barry Gilbert invented this this topology, you could call it, for analog multiplication. Okay, long time ago, like 40 years ago. Okay, let's take the simplest case. Okay, this is your signal, and you have a DC plus signal going through a differential pair. Okay, and you have some differential output current I out. Okay, so what we are going to assume is large enough to switch the currents completely between the 2 sides. Okay, we are going to assume that the differential pair is a perfect switch with respect to VLO. Okay. So that means that you can actually represent the circuit by, so it switches back and forth between these 2 points, and you have your IDC plus IRF here. Okay. What will the output current be? Is your input current. So this is your input current times SFT. Okay. What is SFT? Yes. Okay. Because all it does is it just switches the current one way or the other. So it's a signum function of your LO signal. So in other words, if your signal cosine looks like this, something like this, okay, whatever, okay, so you get the idea. Okay, it's a square wave, it's supposed to be a symmetrical square wave, okay, and it goes between plus or minus. So the definition of signum function is when the signal is input is positive, it is plus 1, input is negative, is minus 1, when it's 0, it's 0. Okay, so it's going to be a perfectly symmetric square wave. Okay, so note, so this is going to be I out, which is the differential signal. If you consider only the single ended signal, okay, I out 1, so that is going to get multiplied by let's say some S prime of t, you can represent it S prime of t because the it's going to look like this. Okay, it's going to switch between 1 and plus 1 and 0, right? Half the cycle it's going to have the current, half the cycle it has no current. IDC IRF times okay. So what does this show you? So this IRF times 0.5 will give you an RF feed through component. Okay. Okay, so what will happen is I out 2 will have minus 0.5 IRF. Okay, so if you look at the differential signal, you won't have this term anymore. Okay. Okay. So what that, okay, so the reason I am telling you this is obviously what that means is if the two transistors, two sides are perfectly matched, then you are going to get no RF feed through. But if you have matching issues, if there is a mismatch between the two sides, then you will get RF feed through. Okay, in the single balance mixer. Okay. Now let's take the case. What times? So what we'll do is we'll try to find out the frequency components of the through the Fourier series. Okay. Okay. So let's try to so your TLO is 2 pi over omega LO Use your S of t. Okay. So actually let's try the DC term also. Huh? In this case DC term happens to be 0. Okay. Okay. 1 to infinity. This is a general term. In this case, A0 is 0 because your DC averages of S of t is 0. Okay. Yes. 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 And we are going to look at to see what happens from IDC. No, in this case you are switching the why would only the signal part change? So if you look at this, the total current is getting switched. IDC plus IRF is getting switched between the two sides. Okay, it is no longer signal is applied here. This is their signal. Remember, it's always the case that RF is always a signal which you are trying to translate to IF. Okay, that is always a desired signal. Okay, LO is just another signal you are using to translate, do the frequency translation. Okay, so A0 is 0. Okay, what is this? This is also 0. Okay, all the cosine terms will also be 0. Okay, because obviously because signum is an odd function, we already know that. Okay. So this will be nothing but 4 over TLO, integral of 0 to TLO by 2. Okay. Right? What is this? Oh, sorry. Of course, right? You'll have an integration in this thing factor. You'll have 1 minus cos n pi. So if n is even, Bn is 0. Okay. If n is odd, it will be 4 over n pi. Okay. So what does it mean for S of t? You can write it as okay, so you're going to have the odd terms and the magnitude of the odd term keeps going down as 1 over n. So what is I out of t? It's nothing but times this guy. Okay. So let's write three terms. One is IDC times each one of these. Okay. What does that give you? It will give you 4 IDC over pi sine omega LO and then 1/3 sine 3 omega LO and so on. Those represent the LO feed through terms. Okay. Okay. So So it's actually not just LO feed through, it's a feed through of LO and its harmonics. Okay. Okay. What is the second term? For IRF over pi cos omega RF t sin omega LO t plus we'll just take the first and third terms for now. Okay. So again cos A sin B you can write it as in terms of the sum and difference terms. So yes, somebody had a question? No. Okay, so that is your first term, omega LO minus omega RF, omega LO plus omega RF. So let's assume that this is the desired term for now. So this is called your lower sideband, this is called your upper sideband. So you'll get 1/3, sine of 3 omega LO plus or minus omega RF. Okay, 5 omega LO plus or minus omega RF and so on. Okay, so what we can see is the higher order terms can be filtered out. They are quite far away. They are at least 2 omega LO away from your desired signal. Okay. So next let's calculate the conversion gain of this guy. What is the conversion gain of this guy? It is, so 4/2 2 RF over pi over input signal amplitude was IRF. So the conversion gain of this guy is 2 over pi. Okay. Okay. The other thing to note, so let's say you're designing a transmitter, okay, and you're interested in one of these. It could be this guy. Let's say you're interested in this guy. Okay. Again, you can filter out the higher order terms, but you should just remember that in this case RF is not high frequency, it's your baseband frequency. Okay. So you're trying to translate it from baseband to higher frequencies. Okay. Which means your actual magnitude of omega RF is very small. Okay. And that means that omega LO minus omega RF and omega LO plus omega RF will be very close to each other, which means filtering could be a problem. Okay. Okay, so let's try to plot out this guy. So we know that we only have odd terms, right? So omega LO, 3 omega LO and so on. So remember that IDC times the signal is going to give you LO so it's going to give you this. Okay. These are your desired omega LO plus or minus RF. Okay. Similarly, you're going to get, remember we got 3 omega LO plus or minus omega RF and so on. Okay, and one of these is going to usually going to be the desired term. Okay. Okay. What else do we know? We assume that perfectly, right? We assume that VLO switches the current perfectly. Okay, but suppose it does not. So let's say SFT was not perfectly symmetric. Okay, so to give you an example, you could have a case where both transistors could be conducting for part of the time. Okay, that is basically wasted power, because what that means is that doesn't go into your switching power, so it will be like an extra IDC term. Okay, so your conversion gain will reduce. Okay, and here obviously if your conversion gain reduces, your noise figure increases. Okay, what else do we know about this? It has very poor isolation between LO and IF, right? So we started off wanting good isolation between all 3 ports, but we know that you get these LO terms at the output. Okay, okay, what else do you know? The other disadvantage, input is the current. Okay, we assumed IRF, so which means you need to convert. So typically the signals coming in from your LNA would be voltage based. Okay, so now what that means is you need a good transconductor. Okay, and usually they won't be perfect. You'll have linearity issues, you'll have noise issues and so on. Okay, so we'll get into that next class. We'll start off next class with transconductors and then move on so first what we'll do is we'll find out how to do this, then we'll find out what you can do about this. Okay, so we'll do those 2 things, and then we'll move on to find out what else we can do with the transconductors, so whether there are other techniques to linearize your GM. Okay, so we'll stop with that here.